Hi everyone. I wanted to just do a follow-up video doing a couple of example problems from the practice problem worksheet that I gave everyone. So these aren't going to be homework problems. These will be other problems that you already have the answer key to. I've had several students say they're struggling with the homework. I think where this is coming from, because I've fixed a couple of problems with other students, I think it really comes down to understanding skeletal structures. So I said from the beginning that I would be using skeletal structures for the rest of the semester. Not just, well, A, because it's easier to write, and B, this is the way you will see almost all molecules written. Using the explicit structure is actually quite uncommon. So I know a lot of the examples we did on the slides as we were going through lecture had explicit structures, but I would always draw them as skeletal structures. So maybe going through this video will help students become a little bit more comfortable with the skeletal structures. But this does go all the way back to chapter 11. So another thing I would be recommending as well, and this is across the board on all of my classes, if you are not reading the textbook at least twice, that's not enough, especially for organic. And when I mean reading, it doesn't mean reading like a novel. I mean reading one sentence at a time and asking yourself, does that sentence make sense? And then only when it does, move on. Or if you really can't figure it out, move on and see if you can get context clues in the next one or two sentences. So just passively reading the book is not going to be enough. Definitely active reading of the book. If you've been doing that, I don't want that to sound condescending. I'm just trying to think of ways that might be able to help people. So book, that would be the first place I go. I haven't checked the views today, but as of 2 days ago, the video count on YouTube was pretty low. I'm talking like 12 views, and there's 40 of us in class. A lot of those actually come from me rewatching the video too. So I haven't checked the numbers. Maybe people have gone back and looked at them. I would also recommend that. And then I've sent out other YouTube videos, maybe if the way I explained it wasn't well enough, that's why I've attached other links. So like giving you the guide on how to name compounds, right? Written from someone else's perspective. Or when I gave you like that YouTube video from another person who talks about converting explicit structures into skeletal structures. So I know it's a lot of work, and I'm not meaning to overwhelm you. If you ever heard any rumors, this is why Orgo is hard, right? It's because I give you one example, and then instead of just being like Gen Chem, where it's like, we can have one equation and I can kind of see how it always works the same. In Orgo, that's not the case. I give you one representative example, and then it becomes pattern recognition, right? So there is a lot of work on both our ends, right? So it's a lot less passive doing Orgo. So enough of me talking about that. Why don't I get into talking about how to solve the problems? So I'll go through, I've just taken a couple from every section, one or two, that I thought would be a good example to do. So I'm just gonna go through in order on how to attack these problems. So these are just screenshots, so that's why it still has like my handwriting somewhere on there, but I'll go through it step by step, right? So step one, right, and this will go for everything. Find the longest carbon chain. And we remember, if we're looking at a skeletal structure, and I'm not going to do this for all of them, I'll do it for the first one, right? At the end of a skeletal structure, there's 3 hydrogens, right? Every single vertex is a carbon atom, and we know carbon can only have 4 bonds. And so that's why it's going to be up to you to fill in the rest with your imagination, literally, right? And the rule is you're filling them in only with hydrogen. So what I'm showing up here, when I drew those 3 lines, that's insinuating that there's 3 hydrogen there. If I go to carbon 2 on this molecule, I see I have 1, 2, 3 bonds already. So that means that carbon must have at least 1 hydrogen to satisfy all 4 bonds. And then I can keep going through the rest of the structure. This carbon 3 has 1, 2. So it's implied that there are 2 hydrogens on to complete the 4 bonds, right? We see on this 4th carbon, 1, 2, 3, And I will put in that fourth bond as a hydrogen, and then we see both terminal hydrogens here are also going to have 3. So you can see already why having the hydrogens explicitly drawn in becomes a lot more crazy to deal with, right? So you can go through, if it helps you, especially in the beginning, to do that. But now you can see it's a lot more cleaned up when you use the skeletal structure. So let's follow our first rule. Find the longest carbon chain. This is usually guess and check, right? When I do this, I just kind of go back and forth and ask myself, I go, if this is kind of written vertically, I'll go down first. So 1, 2, 3, 4, 5. That works. And then you ask yourself, it wouldn't really matter if I went that way. I could also do it in reverse. 1, 2, 3, 4, or 1, 2, 3, 4, 5, right? We're counting every vertex. So you basically get the same structure. So both upwards, it's guess and check. So I see I have 5, so I know it's going to be pentan. It's going to be pentan something. Well, I'm going to be looking for rule number 2, priority substituent, or the one that changes the name. And more specifically, changes the suffix, right? Suffix is the last part of a name. Prefix is before the name. Maybe a new term is infix, which that's everything in between the prefix and the suffix. So right now we're asking, what's the suffix? That's going to be my primary substituent. And so what that really means is, what is my functional group, right? So for us, alkyl groups and halogen groups, or halides, those don't change suffixes. Those are the only two. Every other thing that we deal with, every other functional group will change the suffix. So if I'm not looking at the methyl group, I'm not looking at the bromine, well, then that means I'm dealing with an alkane. How do I know it's an alkane and not an alkene or an alkyne? Because alkenes have double bonds and alkynes have triple bonds. So I know I'm dealing with a pentane. Then what I need to go through is number my carbons so that I have the lowest number attached to the substituents. So I could go this way. I have 1, 2, 3, 4, and 5. My other option is to try naming in reverse. 1, 2, 3, 4, and 5. Right? Now I have to make a choice. My choice is to keep my numbers as low as possible, but we can see it doesn't really matter right now because I have things hanging off. Either it's going to be called a 2 or a 4, or a 2 or a 4, right? So the way we want to go with it is give the higher priority substituent group, right? We said our alkyl groups, which are methyl, ethyl, propyl, whatever, those are on the bottom. So I want to give my bromine the lowest number, which will be 2. So I will keep those numbers of 1, 2, 3, 4, and 5. And so then I go through and name it. I already realized it's a pentane is going to be my suffix. I realize I have a 2-bromo, that's here. I have a 4-methyl. And now I need to plug these phrases into the name. The way we determine the order is not numerically, it's alphabetically. So I can see the bromo comes before the methyl, has nothing to do with 2 coming before 4. So 2-bromo, 4-methyl pentane. And again, hyphens only come between numbers and letters, and that's why methylpentane becomes one word. So that was a little bit overkill in the explanation. I'll go a little bit quicker for the rest, right? But we get 4-bromo, 2-methylpentane. So now let's take an alkene example. So again, the first thing I need to do is find my longest carbon chain. 1, 2, 3, 4, 5. Another rule is that longest carbon chain has to go through the double bond or a triple bond. So basically that starts, if you start to see double bonds, triple bonds, it's dictating what path you need to take. So I had to go through that double bond, right? When we're naming alkenes and alkynes, same rules apply. I got to number them. I have to number them in such a way that my substituent groups have the lowest possible number. So I could go 1, 2, 3, 4, and 5. And if I did it that way, and I'll keep it in red, it would be 2-chloro. And then the way we name the double bonds, if you start at the 4 and you're going through the 5, so we'll call it a 4. I'm going to call it a 4-ene, just to say it's a double bond, right? I could also go through and number it in reverse. 1, 2, 3, 4, and 5. And in that case, I'd have a 1-ene. I'd also have a 4-chloro in that direction. Now I got to choose which one keeps my lowest numbers. 1 and 4 is lower than 2 and 4. Another thing that also backs that up is that the double bond is going to take precedent over the halides. So, I mean, if we were going to make a list, I would call it, our real functional groups, the ones that actually are something other than bonds. So we'll have functional groups, halides, those are the bromine, the chlorine, the iodine, and then alkyl. That would be methyl, ethyl, propyl, etc. So that's in terms of high priority to low priority. So that's why functional group, I'm going to call the double bond a functional group. So every ene. So we know we're going to be labeling from one, basically where the blue is on that molecule. So let me get rid of some of that clutter. Wait, so 1, 2, 3, 4, and then 5, right? So we go through. We can see now we have 5 carbons long. So we know, again, it's going to be base pent. I have a double bond, so it's going to become pent. Instead of pentane, it'll become pentene, indicating there's a double bond. I need to indicate where the double bond is. It's going from 1 to 2, so I'll do 1-pentene. I realize I have also, I guess I missed a group as well, sorry, the methyl group. I have a 3-methyl and a 4-chloro. So I go through, figure out alphabetically, C before M. So it'll become 4-chloro, 3-methyl, 1-pentene. So the long names shouldn't worry you. It just, it's just the name. You just got to put the pieces together. They're like Lego blocks. They just kind of build up. So we got 4-chloro, 3-methyl, 1-pentene. Alkynes are a little bit weird because of the way they're drawn. They're actually drawn with roughly correct geometry. So when you have a triple bond, things are linear. And so what I've been trying to do with my drawing is to leave a little gap so you can see that there is a carbon there, rather than drawing something that looks like this. Because a lot of times you'll see things like that and it gets a little confusing. So again, we're going to follow our same rule. We've got to find the longest carbon chain. 1, 2, 3, 4. That's pretty much our only option. The options we have in terms of numbering are 1, 2, 3, 4, or 1, 2, 3, 4. We see that we have an alkyne, so that's going to be our functional group that takes precedent. So what do I want to do? Well, I want to give it the lowest number. Either it's going to be 1 or 4. So it's definitely going to be 1. So I'll stick with the red. So I know it's going to be 4 carbons long. So it's going to be bute. It has a triple bond, so it'll be butyne. The triple bond is from 1 to 2, so it's a 1-butyne. And then the only other substituent I have is the 3-iodo. So 3-iodo, 1-butyne. So a lot of it comes down to the same thing, right? Longest carbon chain must pass through high priority functional group. right? Keep substituent numbers as low as possible. And I guess number 3 is order substituents alphabetically. Right, so those are our 3 main rules. That's how we're going to go through literally the rest of the problems in terms of naming. So I'm going to try to pick up the speed a little bit on this because I don't know if it's too much or too little, but I want to make sure we keep moving to not overwhelm people. I find it a little easier to go from names to structures rather than from structures to name because it's a little bit more, not organized, but a little bit more structured in how you're going to do your approach. First, you always take a look, what is going to be the length of my longest carbon chain? Decane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ane means it's all single bonds because it's an alkane, so I'm done with my longest carbon chain. Now I just start going through and ask myself what's connected. Well, I have a 3-chloro, so let me put that in. 1, 2, 3. Chloro, done. Then I take a look at my last one, 6-methyl. 1, 2, 3, 4, 5, 6. You can write CH3 if you want. Usually it's just a straight line. We do that in the same color, right? That is typically the way you would draw it. I'll be fine if you put CH3. That's fine. So there's my 3-chloro 6-methyl decane, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have 3,5-diiodo 1-heptine. Again, follow the same process. Hept is 7. So 1, 2, 3, 4, 5, 6, 7. I have a triple bond at the 1 position. So usually, so I'm just kind of drawing this, I'll accept this for us. Typically the real way to do this, because all triple bonds are going to have to be linear. So it'd be 1, 2, 3, 4, 5, 6, 7. It would actually look more like that if you Googled it, just to keep the 180 degrees linear structure of a triple bond. I'm not so worried about that right now. I'm more worried, can we name it? So I'll be fine with the structure I have here in blue. So we have our 1-heptine, and then I see that I have 2 iodines, so diiodo, and one is at the 3 position, the other is at the 5. So I have my 1, 2, 3 iodo, 4, 5 iodo. And I'm done. 3,5-diiodo 1-heptine. So I mentioned in an email, I think I might have mentioned it during lecture 2, that I'm allowing you to use your representative reaction examples on the exam. However, it's up to you to memorize what your functional groups are. I think there's only 12 or 13 of them, so it's not bad. But I will let you have a reaction cheat sheet. So when I look here, a couple of things that I noticed right off the bat. Hydrogen's a reaction, and then I have a metal catalyst. This is telling me I'm going to be doing a reduction. Or a more common way for this particular reaction, and this is what the book calls it, is hydrogenation. So it's the same word that when you get partially hydrogenated vegetable oils, it's literally this reaction, maybe not with nickel, probably with platinum. Catalytic converters in your car. This is exactly what the catalytic converter does. It's made out of platinum, right? When we're dealing with hydrogenation reactions, right, we listed 3 catalysts that are possible. We could use nickel, which we see in the top, palladium, which I see in the bottom example, and this is why catalytic converters are usually, probably high priority to be stolen from a car because they're made out of platinum, which is a rare metal, very expensive, right? That's also why a catalytic converter costs a boatload. So I notice I have a metal catalyst. I have hydrogen, specifically 2 equivalents. So it just means I have 2 times as much hydrogen as I do this alkyne, right? And so I take a look. All right, I'm dealing with an alkyne. I got 1, 2, 3 carbons in that alkyne. Don't care about the name. If I drew this out explicitly, it would look like this, right? I am adding 2 equivalents of H2. What this is showing me is that 1 H2 could be used to break that first bond. And I'll do this as like an intermediate step. So that CH3 in the end doesn't change. This hydrogen, right, it can be snapped on to that alkyne, that triple bond. Those are the H's from that hydrogen. It basically breaks one of the bonds and then inserts those 2 hydrogens across the bond. So what that would effectively do, if I'm resetting this reaction, that means I've already used 1 equivalent of the hydrogen. That means I still have 1 more left. Let me draw it a little bit explicitly. So since I have 1 more left, I can do that same reaction 1 more time. Add that hydrogen, this H2, the one on the right, across the double bond. So I'm going to have to wipe the screen. But what would that look like? I'll rewrite it a little really quick. Right, so here's that alkene structure. I said after 1 addition of hydrogen, we're adding a second. It's being added across that double bond. So what does it do? It breaks the double bond and attaches the hydrogens. And make sure I get enough. I have too many carbons. 1, 2, 3. There we go. And we end up with this structure here. So effectively, what we did is just you take a look at how many more than single bonds. It can't break single bonds. So I got I have 2 bonds that can be added hydrogens across. So I have 2 equivalents of the hydrogen. It means it just breaks all those bonds. So, oops, let me go back one. Right, if I take a look at this structure here, all that is propane. It's 3 carbons long, all single bonds, nothing else. If I drew that as a skeletal structure of propane, there you go. A little wonky, but right, there's my structure for propane. And so I wanted to do that one explicitly so we can do the other ones a little bit quicker. And so what we see here in this second example is I realize I have 1, 2, 3 double bonds and then 3 equivalents of hydrogen. So it means I have enough hydrogen to break and add across 3 hydrogens across 3 double bonds. This was here to basically just to throw you off. It doesn't do anything. It comes along for the ride. So what ends up happening? Let's see, 1, 2, 3, 4, 5, 6, 7. Everything else comes along for the ride, and all I do is hydrogenate those double bonds. I had 3 equivalents, all of them disappear, they all become single bonds, and I'm in good shape. All right, so I just picked one of the harder ones to name from the next section. So again, we're going to follow our same rules. So we've moved on from alkanes, alkenes, and alkynes, and now we're moving into, I think the next section was alcohols, thiols, aldehydes, and ketones. So I just picked one of the harder looking ones, right? Right off the bat, I can see that my functional group is an aldehyde, right? So when I find my longest carbon chain, it has to go through that functional group. So I have to start here as 1. So 1, 2, 3, 4. Then I can go 5, 6, or I can go 4, 5, 6, 7. So there's my longest chain. 7 beats out 6. So I know I have hept, and that's going to be my carbon chain. I have an aldehyde, so it becomes hept and al. The al standing for aldehyde. And then I notice I only have 1 substituent group. It's got 1, 2 carbons hanging off of it. So now it becomes an ethyl group at the 4 position. So 4 ethyl heptanol. I know it confuses people because I used to do this all the time too. You're like, oh, it's 1, it looks like there's 3 carbons. No, what you're counting here, this thing right here is a bond, right? So there's one carbon, and then it's connected to, how does it keep doing that? 1, 2 more carbons. 2 is ethyl. So 4-ethyl heptanyl. Then we got this beast of a name down here. But actually, again, like I said, it's easier to go from names to structures. Be very rigid on how you attack it. Heptane thiol. It's 7 carbons long, and it ends in a thiol. How do I know it ends in a thiol? Because it's at the 1 position. So 1, 2, 3, 4, 5, 6, 7. I have a thiol, SH, at the 1 position, right? I know it confuses sometimes people to think like when they're counting out how long the carbon chain is, a lot of people go 1, 2, 3, 4, 5, 6, 7, 8. Remember, we're only counting carbons. That S, even though it's at the terminal end, oops, it doesn't count as a carbon, obviously. So when we're counting the chain, it's 1, 2, 3, 4, 5, 6, 7. Remember, there's 2 other implied hydrogens there as well to give that terminal carbon 4 bonds. All right, so I'm taking care of my 1 heptane thiol. Start going through just systematically. 2,2-dimethyl. So there's my 1, there's my 2. Dimethyl insinuates that there are 2 methyl groups, both at the 2 position. Like I said, if you want, you're more than welcome to draw in the methyl group if it helps you. But keeping it like in my answer key, it's much quicker to just keep it, an implied methyl group like that. So now I've got rid of my 2,2-dimethyl. The last is 4-bromo. So keep counting. 1, 2, 3, 4. And on the 4 position is a bromo. Done. 4-bromo, 2,2-dimethyl, 1 heptane thiol is that structure down there. Want to clean it up, get rid of my numbers. And there's my structure. And again, I think in the answer key, you might see I have the reverse image. Remember, molecules are in 3D space. These are one-dimensional representation. If I drew 1, 2, 3, 4, 5, 6, 7 with the dimethyl and then the bromo, both structures I wrote are 100% correct, right? I could theoretically do 1, 2, 3, 4, 5, 6, 7. That structure is also the same, right? Just because it's moved in space doesn't make it wrong. All right, so some reactions, right? Again, we're gonna have to start recognizing what my reactions are. I have a secondary alcohol, I have an acid catalyst, and I'm applying heat. So that tells to me, usually when you see something like, we're heating this up in the presence of an acid, what that usually is telling me is if you look here of an H plus and an OH, H plus and an OH, if I bring those together, it forms water, right? When water comes off out of a reaction, we call it dehydration. So it's almost like breaking that bond, and that H plus and the OH leave is water. So if you break that bond though, right, you're freeing up electrons. They need to go somewhere. So you can either think of it really detailed like I'm trying to explain right now, or you can memorize it. Both are fine. But if that OH pops off and I have extra electrons, that means I need to form additional bonds. So I could either put a bond there, which if you were taking Orgo, you'd find out that's the quote unquote more correct place to put it. There's going to be a mixture of products. That's just going to be what's called the major product. And then you also could form, both are correct. There's going to be a forming of a double bond either here or here. And it depends on circumstances. So it would form both, and then usually as a byproduct, you would also form water. I don't know if the book mentioned that. It might have kept it simple, but water would be a byproduct. What I really care about is could you get those structures right there? So dehydration, we're going from an alcohol to a double bond, right? Number 36, right? We were talking, I don't know, maybe put an X there, I meant to highlight it, right? We're looking at an oxidation reaction. The book keeps it very generic, and I will keep following what the book does. That bracket O can be a wide range of molecules. It's not telling you what it is. It's usually potassium permanganate or potassium chromate or something like that. that are strong oxidation reagents, but we're not worried about that. We just know we're oxidizing it. And our definition of oxidation in organic chemistry is adding bonds to oxygen. At least that's an easy one to memorize, right? Oxidation, my number of oxygens should go up. So that tells me if I'm going to increase my bonds to oxygen, if I lose that hydrogen and make a double bond between the oxygen and the carbon, I've satisfied my requirement of adding additional oxygen bonds. Another definition of oxidation is losing hydrogens, so both fit. Again, this is more just like a trick part of the question. They're coming along for the ride. So what is it going to look like? I go from a secondary alcohol to a ketone, and then the rest of the molecule doesn't do anything, just comes along for the ride. So then I end up with my oxidized product. This particular question is a homework problem, but I had someone specifically ask me about this, so I wanted to make sure I covered it. So it's a free point on your homework if you're watching this video, right? So we're seeing our oxidizing agent, whatever that is, but I know I'm going to increase the number of bonds to oxygen. So I don't know if this was actually explicitly mentioned in one of the videos. One of the slides that I did have this reaction. It's to go from an aldehyde to a carboxylic acid. How is that going to happen? Well, you take a look at that aldehyde, right? So again, usually with high concentrations of electrons, that's where the reactions happen. There's a high density of electrons there. It's just going to plop on an OH. So what I will do, again, the rest of the molecule is just coming along for the ride. So the reason why I included all that extra information is to make sure that we're paying attention directly to the functional group that matters, right? This is the one that's where the reaction's happening, so everything else comes along for the ride, and then I oxidize it to carboxylic acid. So this one is a quick one. We covered it very briefly in lecture, but it is really important. That's why I tried to throw in some extra examples. So we brought this up when we were talking about chirality and stereoisomers and enantiomers. This was right before we talked about enantiomers, which are stereoisomers. But there's structural isomers, right? Isomers being same pieces, structural meaning how they're connected. It's basically telling me, what are my Lego blocks? I got 2 carbons, 2 hydrogens, and 2 chlorines, and I better use them all. So if I start with 2 carbons, right, I could throw in, let's say, a chlorine here and a chlorine there, hydrogen there, hydrogen there. I've used 2 carbon, 2 hydrogen, 2 chlorine. I go through, take a look. Well, it looks like hydrogen's fine. It only has 1 bond. That's what it wants. Hydrogen, again. Chlorine, we've seen with the dot structure, only makes 1 bond, right? Because if we look, there's my dot structure for hydrogen. There's my dot structure for carbon. And there's my dot structure for chlorine. And you can always tell how many bonds a molecule will make from its dot structure, usually. So we can see 1 bond for chlorine, 1 bond for hydrogen, and 1, 2, 3, 4 bonds for carbon. Each of these carbons only have 3 bonds. So how do I get around that? If I put a double bond between them, everyone's happy. Every hydrogen's got 1 bond, every chlorine's got 1 bond, and every carbon has 4 bonds. So let me clean this up. The structure we just drew was that. It's asking me for 2 structural isomers. So I need to make at least 2 compounds that are structurally and chemically different. How can I tell? The quick way, and I don't think I gave you this hint, is to name the molecule. The molecule has a different name, it's a different compound. If I look here, I got 1,1-dichloroethene. That's one molecule. If I rearrange things, I'll keep that center carbon like that. If I put say a chlorine here, and I put a chlorine on the other side, and then fill in the gaps with the hydrogen, I still have C2H2Cl2, but if I name this compound now, I got, let me give myself a little space, 1,2-dichloroethene. But I also have to realize it's across a double bond. And this is the only time we need to worry about this is across double bonds. They're considered trans to each other because they're opposite of the double bond. So it's trans 1,2-dichloroethene. Immediately see it's a different name, we're actually done the problem. We have now two structural isomers. One when the chlorine is on one carbon, the other when they're on opposite carbons, but across the double bond. That also leaves us with a third structural isomer where both chlorines are on the top. So this would now be cis 1,2-dichloroethene, right out of space. So let me make it a little bit more neat, and I want to show one more, I don't know, something to pay attention to. Right, so our structures looked like this. I'll do them real quick. There's our first one. Our second one was the trans isomer. And then we said our third one was the cis isomer. What throws people off, let me just make that neater, is what if I drew this, where the hydrogens both point up and the chlorines point down, right? If I'm comparing that to this, right, they look different on paper. They're actually the same exact molecule. They're just flipped upside down in space, right? The one over here, the chlorines are on the top. The one down here, the chlorines are on the bottom. If you name them, they're both cis 1,2-dichloroethene. Therefore, they're both the same molecule. So just because you draw it different or like differently on the paper doesn't mean it's a new structural isomer. It needs to have a new name. That's the way you can check. All right, so identify each chiral carbon with an asterisk, and then determine if the Fisher projection is an L or D enantiomer. Right, when we're looking for chiral compounds, you ask the question, does it have 4 unique substituents? Specifically, this is a chiral carbon, sorry. Right, so when we look at the Fisher projection to the right, immediately on the top, we can see that that carbon is connected to the rest of the molecule, to an alcohol group. But we also see there's 2 hydrogens. It does not satisfy the chiral definition of having 4 different substituents, so that top carbon cannot be chiral. This carbon here in the ketone cannot be chiral because it only has 3 bonds, so by definition, it is no longer chiral. This cross section in the heads up with a Fisher projection, anytime you see a carbon represented as a cross like this, it's automatically chiral. So because I can see I have 1 unique thing, a hydrogen, a new unique thing, and then an alcohol. They're 4 different things. That means it has to be chiral. And again, we take a look at this carbon. It's the exact same structure as that. There's 2 hydrogens attached to it. Therefore, it breaks the rules over here of having unique substituents. So it can't be chiral. So we have 1 chiral compound in the structure. The last part is asking L or D enantiomer. Remember, L stands for left. D is dextro, which is Latin for right. All you need to do is look at the bottom chiral carbon. That hydroxyl group, the OH, is pointed to the left. It is an L enantiomer. And it's always the bottom one, right? So if I had a lot of chiral carbons, like there's an OH here, and an OH here, and an OH here, and the rest are hydrogen, right? And it's going to make squiggly lines for the rest of the molecule. It's just the last chiral carbon. In this case, you'd have a D enantiomer. It does not matter that this one's pointing left. It's only the bottom one. And another thing we're trying to determine if a compound is, if a sugar or a carbohydrate is an alpha or B butyrotated, right? It basically means, is this hydroxyl, the one that came from originally when the molecule had an aldehyde, wrong place, where it had an alcohol group and then an aldehyde, right? I'm just a simplified structure, right? There's a reaction that closes the ring, so it looks like this over here. We said because this aldehyde group can rotate in space, sometimes it points up, sometimes it points down when that ring closes. When the alcohol group points up, it is beta. With the alcohol group pointed down, it would be alpha. And as you can see, I've already, because I just took a screenshot, the alcohol group in that position is pointed up. It has to be a beta mutarotated, the beta structure of that sugar. All right, a couple more naming problems, and I think we're almost done. This actually might be the last slide. I'm not 100% sure. All right, so now we're moved into, I think this is chapter 14 now, talking about carboxylic acids, carboxylate salts, and esters. So right off the bat, I can see I have an ester because I have that carbonyl, carbon and oxygen directly adjacent to an oxygen, which is directly adjacent to a carbon, right? An ester, oops, I can fix that, has basically a general structure that looks like that, where you have your carbonyl, it's connected to an oxygen, which is connected to a carbon. So I know I'm dealing with an ester. Oh, sorry, not an ester. Yeah, an ester. I'm thinking ether now. Right, so we have our ester. So then we need to, this is not the easiest things to name, right? We need to see, basically divide the molecule in half. One side is the alkyl part, and the other is going to be the carboxylic acid derivative. Right, derivative just means piece of, right? So it used to be a carboxylic acid, so I'm going to call it the how did I spell that? Carboxylic, yeah, whatever, we'll call it. It's carboxylate derivative, that's fine. But as long as we know where it's coming from, it's the side that comes from the carboxylic acid. So we take a look at our alkyl group. We got 1, 2 carbons, so I know it's going to be ethyl. And then the rest of the molecule comes after it. So it's going to be ethyl. Oh, sorry. Well, we take a look. We got the 1, the 2, the 3, and the 4. So right now I'm forgetting the chlorine. So I'm just trying to gain the major parts of the structure, which would be the major structure, this part. So we have a methyl, and then I see I have 4 in the carboxylic acid derivative. So that's going to be ethyl, propanoate, NO8, right? Because it used to be propionic acid, but now it's no longer an acid. It has now been, you have an alkyl group attached to it. So it looks kind of like a carboxylate salt, but it's a covalent compound. So we have ethyl propanoate. And then we got to put in our 2 chlorine. I've run out of space. I should have written that smaller, but I see it's 3,3-dichloro. And then we have ethyl propanoate. This one is tough. I'm not going to give you one like that. I realized when I wrote it, well, actually, no, when I was doing the answer key, I said, ooh, this one's not going to go well. That's fine if you can't do this one. Simple esters is what I would care about. What I mean by simple, if you got rid of the chlorines, could you name that compound? All right, I believe this is the last one. Let me just double check. I think it's the end of the slideshow. It is. All right. So in this one is a little bit of a challenge, but it's not that bad. Again, we just recognize what's going on. We see we have 3 carboxylic acids. They happen to be on the same molecule. I happen to have 3 bases. This is just as simple as our old high school reaction of taking an acid with a base, and it creates a salt in water. We're going to get the same reaction happening below. What's going to happen? Well, my salt is going to look, I don't have a lot of space. I have to erase what I just wrote down, but it'll be the same idea. My acid is going to lose all of its hydrogens, and it will join up with those 3 hydroxide. So I know 3 water will be formed. That's going to leave me with, let's see if I can do this without taking up too much space. There is my carboxylate. It basically lost all its H's. And so the only thing I have left are going to be those 3 sodium cations, and they just go in to balance out the charge. So I'm not expecting you to name this one because you have 3 carboxylic acids on the same compound. But again, you just take a very structured approach to it. It's the same thing as hydrochloric acid reacting with sodium hydroxide, all the way back to high school. It forms a salt. Here's my salt and water. This is a challenge problem. But again, if you saw 1 carboxylic acid and then 1 equivalent of some kind of strong base like sodium hydroxide in this example, or potassium hydroxide, the KOH, right? Would you be able to predict the products? All right, so that ends that. Hopefully that wasn't overwhelming. It's longer than I intended it to be. I thought it would be a little quicker to go through, but hopefully if you even go through and pick and choose the things that were throwing you off, hopefully it gives you a better sense of being in control of this. I know, again, I recognize it's a lot, but at the same time, like, this is organic chemistry. It does require a large amount of practice. You're going to see things you've never seen before, in the sense that maybe you haven't seen explicitly drawn like that before, but you actually, right now, all of you, every single one of you do have the skills to answer all of these problems. It just might take some going back to the book, going back to your notes, rewatching videos. All right, so I think we've spent enough time on that. So hopefully this helped out a bit. And I will talk to you hopefully later tonight. I'm going to run the review session at 6 o'clock. I'm sending out that email right now. I will talk to you all later.